Hello everyone. In today's lesson we are going to move along in the branch of E&M and we're going to finally look at the M part of E&M, which stands for magnetism. In this lesson we're just going to start with the basics, which would be starting with a magnet. Alright, so I'm going to show you a couple little demos just to make sure we're on the same page for what a magnet is, what it kind of does, and then we'll be able to get more in depth with later lessons. Alright, so let's take a look at some magnets and what they do. Okay, so here we have a magnet. Super exciting. So what do magnets do? That'll be the first question we answer. So if I have a magnet here and I bring another magnet near it, all right, let's see what happens. So that thing obviously attracted the other magnet. Likewise, notice I just flipped the magnet, and if I push it this way, it repels it, almost like magic. All right? So it can repel it without touching, and it can also attract it without touching. So the idea is that magnets exert forces, but not necessarily that simple. Because if I bring another object near this, all right, notice that this magnet does not have any effect on this. So what we say is, what we say is magnets exert forces on other magnets. All right, that's what they do. Magnets exert forces on other magnets. Okay, so the next question is, what do magnets have? Well, if you couldn't see before, here it is a little bit closer. All right, notice this magnet has an N on one side and an S on the other side. This refers to a magnet's poles. All right, we call them magnetic poles, and they had the name of North Pole and South Pole, and I'll talk about that in a sec on how they got their names. All right, so that's what magnets have. You cannot split a magnet and isolate poles. That is different from a proton electron. You can have a proton by itself or positive charge by itself and an electron by itself, but you can never ever have just a North Pole and just a South Pole. If I were to cut this magnet in half, all right down the middle, then this would have a north side and a south side, and this side would have a south side and a north side. All right, so you can never split up magnetic poles. All right, so the next thing magnets have, all right, is, let's get this focused a little bit if I can, maybe not. What we've kind of already seen is these magnets are able to attract and repel each other without touching. Now, we've seen this phenomenon before with the electric force and with gravity. All right, so the question is, how in the world is this object able to exert a force on this without touching? All right, that's a big question. Fortunately, we've answered this already in a different respect. When we talked about electric charges, they were able to exert forces on each other without touching. And the solution to that was the electric field. So you can make the next guess that these magnets have a field that surrounds it as well, all right, going out in all different directions. And when another magnet comes into this magnet, right, this magnet here, if I switch it the other way, this magnet feels the magnetic field from this one, and that magnetic field pushes it away. So what we have on this magnet here is a magnetic force surrounding this whole entire thing. All right, surrounding this whole entire thing. So let's take a little bit more in-depth look at the magnetic field. Okay, so let's first place down a magnet. All right, and what I'm going to place over top of that is a piece of cardboard with a piece of paper on top. Now, remember, the magnetic field is still there. There's a magnet underneath, so there's a magnetic field here. What I'm going to do is I'm going to sprinkle a whole bunch of small magnets that are going to get affected by this magnet's magnetic field, and they're going to get caught up in that shape. All right, so let's see what shape the magnetic field has around a regular magnet. All right, you can already see it start to come into shape. All right, notice there's like magnetic field lines like we had electric field lines. All right, and it should be obvious on where the poles of the magnetic field or the magnet are located, there and there, and we can see that it takes the shape all around it. All right, and if I tap this, start maybe could come in, cause a little bit more, get into even more lines. All right, so that's what the magnetic field around this magnet actually looks like, which is pretty wild. All right. Okay, now here's a 3D view of the magnetic field. All right, what I have in here is a whole bunch of the tiny magnets, like I just had there. All right, but with this magnet, we can see. I'm going to put it in the middle. We can see all around this thing. All right, I know it might be hard to see, but if I go down this way, shake this thing around, all right, you can see a 3D view of what it would look like. All right, I know it's kind of hard to see with glares and everything, but that's what the magnetic field looks like in 3D. Okay. The magnetic poles are named north and south for a very particular reason, and that is due to planet Earth. All right, planet Earth is a giant magnet. All right, which means it has a gigantic magnetic field. All right, and there's applications of it. We'll talk about that in a second. So if the Earth is a gigantic magnet, that means it has its own magnetic fields. All right, sorry, it has its own magnetic poles. Now those magnetic poles are located at the North Pole and at the South Pole. All right, so since we have those names of those magnetic poles, that allows us to use a compass. All right, now a compass is just a magnet that's on a pivot. All right, this needle in here is just a small magnet, and this magnet gets caught up in the Earth's magnetic field, just like all those little tiny magnets that I just showed you on the paper got caught up in that magnetic field. So this thing can orient itself into the Earth's magnetic field, and when it does that, one side of the magnet is attracted to the North Pole and the other side is attracted to the South Pole. All right. Now there's one major rule that we haven't talked about yet with magnetic poles, and probably should have done it in the beginning, but we'll do it now. All right, if you didn't figure it out, it's very similar to electric charges. Like poles repel each other, and opposite poles attract each other. So a North Pole will attract a South Pole. A South Pole will attract the North Pole. But two South Poles, they will repel each other. Two North Poles will repel each other. And you've already seen that in the demo. All right? So what happens here is, let's imagine this one has the South and North. If I put this on a pivot, what happens is this North Pole will actually point to the Earth's North Pole. All right? Now, right away, that sounds like I messed up. Why does the North attract to the North? Well, there's a difference between geographic poles and magnetic poles. All right? So I'll show you this diagram here. Okay, so here's a diagram of the Earth with its magnet and its magnetic poles labeled. So here's the North Pole. That's geographic North Pole. This is where Santa Claus lives. Here's geographic South Pole. That's where the penguins live. All right? Now, you can imagine that there's a giant bar magnet inside the Earth. It's not literally, but that's how you can visualize it. And notice when we label the poles of the magnets, that the South Pole would have to be at the north geographic, a magnetic, so let me try that again. A magnetic South Pole will have to be located at the geographic North Pole, because that is why this bar magnet would be attracted to the magnetic South Pole. And in our compass, you can imagine this being a compass, that will allow the north part of the part of the needle that's labeled north to point toward geographic north, and that's how we can figure out where Santa Claus lives. All right, because this thing will point us directly in that location. Likewise, in the geographic South Pole, all right, the south part of a magnet, the south part of a compass needle will be attracted to the north pole of the magnet, all right? So it's actually kind of backwards in terms of Earth. In the geographic north pole, all right, which is here, which is where the axis of rotation goes through, all right, there's actually a magnetic south pole, which allows all of our compasses to point towards north, all right? And so that's how we gotten the magnetic names for all these things, all right, is which way it aligns if we were just to let it pivot, all right? This will point to north, this will point to south. If this magnet had somewhat rotated and it went to east and west, then all of our magnets would be labeled with W's and E's. But it's not like that. So we have the north and south geographics, and that's where it's kind of located, and that's why they get their names here. Notice in here that it is off a little bit. That's called magnetic declination. So a little bit different subject, but the actual magnetic pole is not located directly at the North Pole. So if you were to follow a compass and you would and just follow it blindly without taking magnetic declination into account, it would not take you to the direct North Pole. It would take you pretty far off. I want to say it's like I don't know, 1,000 kilometers. It's pretty far. Maybe that's one of the reasons why nobody ever found Santa Claus up there, because the compasses never lead to where he actually lives. All right, it's off by a lot. But that's how our poles got our name, and has to do with the Earth's magnetic field. Okay. Now we can prove that a compass is a magnet by bringing it near another magnet. Remember, magnets exert forces on other magnets through the magnetic field. All right. So if I bring this compass, all right, near this magnet, it's going to get caught up in its magnetic field. Now I've already drawn the lines of the magnetic field based off the pattern we saw more or less when I sprinkled all the little tiny magnets on here. So this compass should get caught up in there. And let's see. Notice that it spun around and it points right, this white needle points right there. And as I move this around, all right, that white needle moves as well to stay pointed there. All right, I bring this down here. All right, so we have a north pole here, so that means this white part is the south pole of this magnet. If I flip this around, all right, then you'll see the other part of the compass is attracted there. And it stays on the same lines that we saw before, all right? So this compass can help us kind of map out the magnetic field and give us a little bit general direction based off of these northern pole, all right? If I put this in the middle here, all right, it gets caught up between both of them. Remember, this one wants to be attracted there, this one would be attracted there, and it stays in that magnetic field's direction. Likewise, if I spin all the way over here, all right, we have that. And I keep this here. So without this other magnet, this compass will naturally go to the Earth's magnetic field, all right? Now, the Earth's magnetic field is huge because it's the entire Earth, but it's very weak because if I bring this little tiny magnet in here, all right, this little tiny magnet dominates the entire Earth, all right? So there's a nice little demo on how there's all come together. So that's the basics of in the intro to magnetism, all right? What do we know about magnets now? Well, we know they have poles, magnetic poles, that are called north and south. We know surrounding a magnet is a magnetic field that interacts with other magnets, just like the electric field interacts with electric charges, all right? And we know that magnets exert forces on other magnets. They do not exert forces on things that are not magnets, all right? So magnets exert forces on on magnets. And our rule for those forces and poles to bring it all together is very similar to the electric force, all right? I almost said like charges, but like poles attract and opposite poles repel. All right, and attract and repel we know is a force. All right, so the next major question, which we will explore in the next lesson, is what makes a magnet a magnet. All right, where does magnetism come from? All right, some people say I'm a magnet. Well, what makes me a magnet? Well, very good looking, charming, very funny, smart, sharp sense of style. It's a long list, all right? But that's a different type of magnet. I am not this type of magnet. How do I know? Well, the magnet is not attracted or repelled by me, all right? I know it goes away, so I think, yeah, it repels it, but that's just gravity, all right? So this thing is not attracting me. So in that sense of a magnet, I'm not one of those. So what makes this a magnet and what makes this not a magnet? All right, that is a big question that we'll handle in another lesson. All right, so thanks for watching, and I'll see you when I see you.